Okay, now let's introduce a new property about sets, and that property is cardinality. Now, when you hear the word cardinality, you should kind of think in the back of your head, size. That's really what cardinality means, okay? So let's take a set S, and let's suppose that we can write it like this. S equal to x1, x2, x3, and so on up to x sub n, okay? And let's further suppose that the x sub I are all distinct. So x1, it can't be equal to x3, for example, okay? So in this case, we say that the set S is finite. Why is it finite? Because it has a finite number of elements, right? And we say that the cardinality of the set is equal to n. Cardinality of the size of the set, right? It's got n elements, so the size of that set is n. This is the way that we write cardinality. It's like the absolute value sign, okay? That means the size of S, or the cardinality of S, is equal to n, okay? All right, so that's just the definition, okay? I might as well just kind of define this term too. If S is not finite, what does that mean? It means that I cannot write it as x1, x2, and so on up to x sub n, right? Then it's infinite, okay? So if I can't write it like this, it must be that it keeps going, right? That's what we'll mean by infinite set in this class, okay? You'll see different definitions if you pursue, for example, a course in set theory, okay? All right, so we have this. Now, I will introduce the last kind of operation that we'll perform on sets. We talked about the property, which is size. Now I want to talk about the new operation. And the operation is a power set, okay? And the power set of a set, and we write that using this kind of a funny looking P of S, is the set of all the subsets of S, right? So let's try an example. Let's think of the power set, and let's say that I have 1, 3, and 5, okay? Okay, so what is that equal to? Well, that is actually a set of things, right? So it's a set, okay? And it contains all of the subsets of S. So what are the subsets of 1, 3, and 5? Well, definitely the empty set is one of them, right? Okay? And so is the set that's just 1, the set that contains 3, and the set that's just 5, okay? Those are all the sets that I can make that just have one element in them, right? Now, how many sets can I make that have two elements? Well, let's see, I have 1 and 3, right? I have 1 and 5. I can also get 3 and 5. Okay, great. And how about sets that have 3 elements? Well, there's only one of those, 1, 3, and 5. Okay, and that's it. Those are all the subsets that I can get. You'll notice that I had 3 elements, and I ended up with 8 subsets. And that might make you a little suspicious. 3 and 8. 2 to the 3 is equal to 8, right? You know, so yeah, that's actually the case, and we'll see that. Okay. All right. Now, what do we have? Let's write that definition kind of more mathy, right? And so the set power set of S is the set of all T such that T is a subset of S, right? And as you can expect by now, there's even a third definition, which is also mathy, and we'll say that for all T belongs to the power set of S if and only if T is a subset of S, right? Those two definitions are equivalent, and are both formal mathematical ways of kind of stating the first definition, which is meant to be more intuitive, okay? All right, so we have all this. Let's just make two statements that are, quote, obvious, okay? No matter what S is, okay, the empty set is a member of the power set of S. Now, why is that always true? Well, we proved that earlier. We proved that for all S, the empty set is a subset of S, right? Since it's a subset, it must belong to the power set, okay? Now, what else do we have? S also belongs to the power set. Well, S is a subset of itself, and the subsets of a set are the elements of the power set. So yeah, both of these statements are in fact true. And think of that as kind of the smallest possible power set. It has to contain both of those. Okay, so let's talk about cardinality of power sets, okay? That's kind of the reason that we introduced these two notions at the same time, okay? So let's say that S is a finite set and has n elements. What is the cardinality of S, okay? Well, here's how we're going to find it. Suppose that S is the empty set. Then what are the subsets of the empty set? There's just one. It's just the empty set. So when S is the empty set, I get back cardinality of the power set is actually 1, okay? Let's say that S contains just one element, call it x1. So what's the power set? Well, the empty set belongs to that, right? And so does the set S, right? Because that's one of its subsets. So here we have kind of n here is equal to 0, right? And the power set of S, the cardinality of that, is equal to 1, right? Here we have n, which by the way is just the cardinality of S, is equal to 1. The cardinality of the power set is equal to 2. Okay, so we have a pattern going, maybe. Okay, so let's look at our next example. S now has two elements, x1 and x2. What's the cardinality of the power set? Well, the power set, I have two elements, right? So might as well always start with the empty set. We know that's in there, okay? And now let's think of the sets that have cardinality 1, the subsets cardinality 1. Well, that's just x1 and x2, right? And then the subsets of cardinality 2, well, there's only one way to get 2, and that's to have all of them. So this time, the cardinality of the power set is equal to 4, okay? Let's kind of collapse all that into a slightly different way of thinking, okay? So here's the way that we're gonna find the powers, the elements of the power set, or the subsets, right? We're enumerating them, right? So we're discovering all of them. So what I'm going to say is that you get to make n decisions, right? And the decisions are, if I'm building a subset, do I include x sub I or not, right? And there are n x sub I, x1, x2, x3, up to xn. For each one of those, I get to make an independent decision. Do I want to include x sub I or not? Okay, so n independent decisions. A decision could be true or false. So let's use the numbers 0 and 1 to kind of decode that. And let's write the decisions and how they might look. Okay, so let's say when n is equal to 3, here are my decisions. 0, 0, 0, that means I don't include any of them. 0, 0, 1, that means that I include only the last one. I'm going to say that's x1, and there's a reason for that. How about 0, 1, 0? Okay, well, I'll say, yeah, okay, so I include only the second one, right, x2. 0, 1, 1, I'm going to include x1 and x2. 1, 0, 0, I include x3, but not x1 and x2, and so on, right? So I kind of have 3 digits, right? They're actually binary digits or bits, okay? And each one of those gives me a different subset, okay? So how many do I have total? Well, the real question is how many different numbers can I encode with 3 bits? And as you can see here, right, there's actually 8 of them. I go from 0 to 7, so there's 8 all told, okay? We saw that earlier too, right? I mean, that's exactly the number of elements that we looked at, okay? So what's the cardinality of the power set of S? That's the number of numbers that I can write with n bits, and it's actually equal to 2 to the n, right? So yeah, that's the cardinality of a power set, right? If I know how many elements are in the set, let's say there's 10, then I know that there are 2 to the 10 elements in the power set, right? So great. Now we have a way of doing that. I want to take a different approach to what we just did. This is kind of a different way to analyze the same situation. And this time what I want to do is I want to prove something that's a lot weaker than what we just said. We know that the cardinality of the power set of S is equal to 2 to the n if the cardinality of S is equal to n, okay? And 2 to the n is always bigger than n, at least when n is equal to 0, 1, 2, 3, and so on, which are the valid values for cardinality. So now what I want to show is something weaker, which is just simply that the cardinality of the power set is larger than the cardinality of the original set, okay? So how am I going to do that? The key is to construct this table. Okay, so I have a table that has the elements and the subsets, okay? And the assumption here is what if the cardinality of the power set was actually equal to n, so that the power set is the set of S1, S2, S3 up to n, right? Notice that it's the same n as the x sub I and the s sub I, right? So if that's true, then I can line them up like this. So I have n rows, right? And what I'm going to do is I'm going to show you that, in fact, I can't do that, right? Because I'm going to find some new set, S prime, okay, this is a new set that is actually in the power set. It's a subset of S, and it's not one of the S sub I, okay? So notice a couple of things that I'm saying. I'm saying that same cardinality, okay, is the same thing, is actually the same thing as a lineup in a table, okay? And in fact, that's kind of an idea that I want us to have when we talk about two sets having the same cardinality. It means that I can line up their elements in a table, just kind of one to one, like that. Okay, so here's how I will construct this new set S prime. And what I'm doing is I find the set of all x sub I, so that x sub I belongs to S. Okay, so it's one of the elements of S, but x sub I actually does not belong to the set S sub I, right? So here is x2 and S2, means that x2, if x2 belongs to S2, then x2 will be in S prime, otherwise it will not. Okay, now this is kind of a tricky thing. Okay, so let me show you what I mean. Let's say that S is equal to the set, I'm going to make it 1, 2, and 3. Okay, and I'm going to line them up in this way, so I have the elements and the subsets. And so the elements are easy. That's just 1, 2, and 3. And I'm going to claim that the power set actually contains only 3 elements. So let's say that this is the empty set, this is the set 1, 2, and this is the set, let's just say the set that contains 2, right? I claim that this is all of the subsets in a power set. Of course, that's not true, but that's the point. Okay, so how am I going to find S prime? Okay, well, S prime is equal to the set, and I'll go through each one of the elements. And so the first question is 1 in the empty set, right? That's a question. And the answer, of course, is no, right? So since it's not in there, then I'm actually going to put it in the set S prime. Okay, all right. So now the second question is 2 in the set 1, 2? And the answer, of course, is yes. Okay, so I'm not going to put 2 here. Okay, I'm not going to put 2 in S prime. 3 is 3 in the set 2, and the answer is no, right? So I'm actually going to put it here, right? So this is my set S prime. Okay, now notice that is not any of these, right? So S prime is not here. Okay, and the reason is pretty clear. You see, S prime is not equal to the empty set, because S prime contains 1, but the empty set does not. Okay, S prime is not equal to, by the way, this is of course S1. S prime is not equal to the set 1, 2, which is S2, because the number 2 actually belongs to S2, is in 1, 2, but is not in S prime, which is 1, 3. And finally, S prime is not equal to the set 2, which is S3, because now all I have to do is look at the number 3. 3 is in S prime, but is not in S3. Okay, so that's how I can always construct this new set that isn't one of the ones that we were looking at. Okay, so let's see the kind of formally for any set S, right? I have the set S prime. It is the set of all x sub I such that x sub I belongs to S, right? So it's one of the elements of S, but it is x sub I does not belong to the set S sub I, right? Which is the set that's in the same row and in this table. Okay, so it's pretty obvious that S prime is a subset of S, right? Because all of the elements in S prime, they have to be one of the x sub I. So those are the elements of S. So yeah, this is true, right? But S prime is not equal to S1, and to do that, all I have to do is look at X1. If X1 belongs to S1, then it doesn't belong to S prime. If X1 doesn't belong to S1, then it does belong to S prime, right? So that element X1 is in one of S prime and S1, but not in both, okay? The same goes for any of the other S sub I, right? X sub I belongs to S sub I or to S prime, but not to both, right? So it's a new subset, right? So what we have is that I have a subset that is not in this table, right? So that the subsets can't be put in a table with the elements of S, right? And that's exactly what it means to say that the power set has a different cardinality than S, right? It has to have a larger cardinality because it's the one that kind of runs out of rows.